The next distribution we'll consider is the exponential distribution. So a random variable x is distributed as exponential with parameter lambda, and lambda is also a parameter we see in the Poisson random variable, but this will be a different lambda. It's distributed with this exponential lambda if it has the following PDF. So I'm just going to give you the PDF right away, and we'll consider we'll derive the expected value, the variance, the MGF, and then we'll see some interesting properties about this guy. Okay, so the PDF is given by this. So again, we'll do our standard form. F big X little x is equal to, and again, it's going to be two things. So it's going to be lambda e to the negative lambda x if x is bigger than or equal to 0, and 0 otherwise. Okay, so this is only defined for non-negative values of x. So, and then 0 otherwise. So if we draw a quick graph, it looks a little bit like this. So lambda e to the negative lambda x. So given that lambda has to be positive, which is another restriction here, we see that it'll look like this. So if we just say lambda is 1 for simplicity, then it's just going to be e to the minus x. And we know how that looks, right? If we have 0 and this goes out to infinity over this way, then e to the minus x looks like e to the x reflected across the y-axis. So it simply just looks like, we start here at 1. It'll just taper downward just like that. Okay, so and if we increase lambda, then this just kind of changes the shape of this guy for us. And to do a quick reality check, we should definitely check that this PDF does integrate to 1 over 0 to infinity. So if we take the integral from 0 to infinity, and inside we want to put lambda e to the minus lambda x, let me pull lambda out, e to the minus lambda x dx, then we get lambda out front. This e to the minus lambda x integrates as minus 1 over lambda e to the minus lambda x evaluated from 0 to infinity. So we're going to have to do a lot of these e to the minus lambda x 0 to infinity calculations here, so it's important that you realize how to do them. So this computes nicely. This is minus 1. Now we have e to the negative lambda infinity. So we have e to the minus lambda infinity, and since lambda is positive, that's really e to the power of a negative huge number, and that becomes 0, as we see from the graph, right? It tapers down towards 0. So really that's 0 minus, and when we plug 0 into here, we get 1. So we get negative 1 times negative 1, which is 1, which is good. That is what we're supposed to be getting. So we see the integral under this whole graph is indeed 1. Okay, so let's go ahead and calculate the three things we usually calculate: expected value, variance, and MGF, and then we'll talk about a few cool things about this distribution. They're not too hard to calculate. We want to find the expected value of our x. That's going to be integral from 0 to infinity. Remember, I'm just taking shortcuts now. Really, it's integral from negative infinity to infinity, but we see that if we were to extend this over here, by our definition, it would have to be 0 everywhere else. So this would be just identically 0, so there's really nothing to integrate there. Okay, so we just have that integral, and it's going to be x lambda e to the minus lambda x dx. Now, this is going to involve integration by parts. So first, let's pull the lambda out front, and we're left with the integral 0 to infinity x e to the minus lambda x dx. All right, cool. Let's use integration by parts. U equals x, let's say dv equals e to the minus lambda x dx. Okay, so v must equal negative 1 over lambda e to the negative lambda x, and du equals dx. Putting that together, we get uv minus v du. So uv is x times this quantity, so it's minus x over lambda e to the minus lambda x minus v du. So we get v, and du is here. So minus with this minus 1 over lambda becomes a plus 1 over lambda. We get e to the minus lambda x dx. Okay, nice. And let's put our bounds in. So this is from 0 till infinity. And again, this, a cool thing about these general calculations we'll see right now. So this has to also be evaluated from 0 to infinity. But let's notice something. If I plug infinity into this guy right here, then I'm going to get negative infinity over lambda, e to the minus lambda infinity. So that seems unclear at first. Let's do a little side trek over here. So we have minus x over lambda, and I'll put this e to the minus lambda x in the denominator, so it's e to the lambda x down here. Now, what grows faster? x or e to the lambda x. E grows faster, and we can see that just by a simple graph. Here's x's growth rate, the graph of x, and e to the x grows like that. It grows exponentially, right? So that's the graph, and we see that e to the x grows very, very, very fast. So this is going to dominate this term, and this is going to go to infinity much faster, causing this whole to be 0. So plugging infinity into here causes 0. If we plug 0 into here, we get 0 also, because the numerator becomes 0. So this term almost always in this general form will go to 0, and we won't have to worry about it at all. All we got to worry about is this part right here. Now this we've actually seen. What is this integral right here? It's the integral from 0 to infinity e to the minus lambda x dx. Where did we see that before? Right here. 0 to infinity e to the minus lambda x dx. And what did we find that was? That turned out to be, if we follow it down here, it turned out to be negative 1 over lambda times negative 1. So let's write that. So remember, this lambda out front we took out in the very beginning still exists. So there's that lambda, there's this 1 over lambda, and there's the integral, which we said was minus 1 over lambda times minus 1. So really this minus minus becomes a plus. So this becomes a plus. We have a lambda, 1 over lambda cancellation, and all we're left with is really 1 over lambda. The expected value of exponential distribution is 1 over the parameter. Okay, cool. So that's pretty easy to remember, and we'll see the variance is pretty easy to remember as well, but it'll take a little work for us to calculate. Now the variance is, remember, using our trusty variance formula, expected value of x squared minus expected value of x squared. Okay, cool. Now this we just calculated, so this whole thing right here is 1 over lambda squared, and I'll put a minus here to signify that minus. So then we need to calculate this. It's done in much the same way. We need to do integral from 0 till infinity of lambda e to the minus lambda x. Now we have to put x squared, because we have x squared up here, dx. So again, let me pull the lambda out, and we'll do integration by parts on this pretty painlessly. So it's e to the minus lambda x dx. Now I say painlessly because a lot of the work is done for us. We have to do the first step, and we know the integral that will come out of that. So this is equal to lambda, and then what we're going to use is our integration by parts. We're going to say u. Where will I do this? I'll do this right up here. So we'll say u equals x squared. We'll say dv equals e to the minus lambda x dx, just like it was before. So we get v equals negative 1 over lambda e to the minus lambda x, and we get du equals 2x dx. Okay, sorry for that bad in the margin here, but we see that what we get is this lambda out front, and then we get uv, so it's going to be x squared, and then v is minus over lambda e to the minus lambda x. This guy evaluated from 0 to infinity, minus v du. Okay, so we have v is right here, so again we have a plus 1 over lambda, and then du is right here. So we have, so doing this integral v du term, we have v right here, and then we have integral of v du is, so we'll put a 2 up here. In fact, we'll put the x, we'll put the e to the minus lambda x, we'll put the dx. Okay, so that's all we have, 0 till infinity. Now we're pretty much done actually, because let's look at this term. Evaluating this from 0 to infinity, we have the same deal we had before with that first term. If you put infinity, the growth rate of this e is faster than the x squared. So this will go to 0 in that case. If you put 0 into here, x becomes 0. The numerator is 0, the whole thing is 0. Again, this thing nicely goes to 0 and doesn't cause us any trouble. So the next thing we have to worry about is, so this lambda and this 2 over lambda cancels to become just a 2. So we have 2 integral 0 to infinity x e to the minus x e to the lambda x dx. Now you might be thinking, oh no, we have to use integration by parts again. But really we don't. We know what this is because we did that calculation for the expected value. That is exactly what the expected value was, right? This is the expected value because it's just x times the PDF. So the expected value we know is 2 over, the expected value is 1 over lambda, sorry. So then this will become 2 over lambda. Cool. So we found that the expected value of x squared is 2 over lambda. So we need to do the calculation 2 over lambda minus 1 over lambda squared. What is 2 over lambda minus 1 over lambda squared? That's going to be... Now the next thing we want to do is calculate the variance of this exponential random variable. So we're going to use our typical trick. Variance of some random variable is equal to expected value of the random variable x squared minus expected value of x squared. Okay, so this we know. We found this was 1 over lambda, so we have to square it. So this is minus 1 over lambda squared, incorporating this minus sign into here. Now this is something new we got to find. So it's not that hard. We just use the formula again. So 0 to infinity e to the minus x dx, and the lambda I'll put out front. Okay, we need to do this. Now this seems a little bit daunting. Maybe we have to do, you're thinking we'll have to do the integration by parts twice. We actually won't, because once we do it once, we'll find something that looks a lot familiar. Okay, so let's go ahead and get started. So we're going to say u equals x squared. dv is going to equal e to the minus lambda x dx again. So this is familiar. So this is just here. We get this, and then we get du equals 2x dx. So we get uv, so we get negative x squared over lambda e to the minus lambda x from 0 to infinity, and we'll see this will cancel nicely, minus the integral of v du. So v, this is 1 over lambda negative, this will become a plus 1 over lambda, and then we'll put all the remaining terms inside here. So we'll get x v du, so we'll get x dx, and actually there's a 2 here. Let me put that up here. Okay, so we have 2 over lambda times this integral right here. Now let's deal with this guy first. Now if we plug infinity into here for x, we see that this e to the negative lambda x, which is in the denominator, will grow a lot faster than x squared, therefore that'll be 0. If we put 0 into here, this will be 0 because x squared is 0 at 0. Therefore we have the numerator being 0. So this again nicely doesn't give us any trouble and just goes to 0 silently. So then we have 2 over lambda, and actually I need to put in this original lambda that was out here. So putting that up here, carrying that over here, we have 2 over lambda, and then this looks very familiar. What is it? This kind of looks like the expected value, doesn't it? Because it's the PDF, or kind of part of the PDF, times x dx. So it's the expected value, except we're missing this we're missing this lambda term over here. So it's actually the PDF, it's the expected value divided by lambda. So what is the expected value? It was 1 over lambda, and we take that and divide it by lambda, we get 1 over lambda squared. So it's 1 over lambda squared. So we actually have some nice cancellations. We have this lambda with this lambda, and we get this is 2 over lambda squared. So that is the expected value of x squared term right here. So all we have to do, 2 over lambda squared minus 1 over lambda squared gives us 1 over lambda squared. So this is equal to the variance of this exponential random variable right here. That's very nice. Now let's find the moment generating function. This won't give us too much trouble either. So what we need to do, we need to find the expected value of e to the s x, where x is our exponential random variable and s is some real number. Okay, so let's just go ahead and tackle this using our normal means. So 0 to infinity, and we're going to put e to the sx, and we're going to put lambda e to the negative lambda x. This is really nice because we have these e terms coming together, and they're going to make life very easy for us. Dx is equal to, I'll pull the lambda out front, and then we have integral from 0 to infinity of e to the x s minus lambda dx. Now this is a very basic integral because this is a real number, this is a real number, so all I have to do is take lambda over s minus lambda e to the x s minus lambda evaluated from 0 till infinity. So I put infinity into here. Now this is a little caveat of this thing. Let's first assume we're in the world where lambda is bigger than s, okay? So that means that s minus lambda is going to be smaller than 0. So that means if we put e to the x, so being smaller than 0 means the graph looks like that, okay? Tapering downward, just like our PDF looked like. So putting infinity into here, we see that goes to 0. So we have lambda over s minus lambda 0 minus, and putting 0 into here, we see that clearly is 1. So this is a negative 1, so we can just flip the denominator, so we get lambda over lambda minus s. And that's going to be our moment generating function under this assumption that lambda is greater than s. So this is actually our MGF. Now let's just explore what happens if that's not true. What if we had lambda is less than s? Well, if lambda is less than s, then this s minus lambda is positive, and the graph doesn't look like that at all. It actually looks like that, right? So considering only starting at 0. Now that's a big problem, because if we plug in infinity into here, that's going to be infinity. It's going to go to infinity, and this won't have a value. Therefore, this MGF is only defined if the parameter exceeds whatever you're putting in there. So you can't put values that are values of s that are bigger than lambda. So that's a restriction that we have to keep in mind. Also, a way to see that is if you did put values that are bigger than lambda, if s was bigger than lambda, then this denominator would be negative. Lambda up here is positive, so this whole thing would be negative. So that you're telling that expected value of e to the something is negative. Impossible, because this e to the something is a positive, always has to be a positive variable. So the expected value cannot possibly be negative. So you know something must be fishy. So here's our MGF. I'll label all these things MGF. Here's our variance, and the expected value was 1 over lambda. Okay, cool. So we found all the major things. Now let's do a few cool explorations into this guy. The first, the major exploration, I guess the primary one we'll be doing, is looking at this kind of example. So let's say you have, this is going to represent time. Let's say time starts someplace at 0, you just at any arbitrary time. And let's say we'll put a time s here, and let's put a time t here. So this is in time interval right here of length t. So we're going to consider two probabilities. First is the probability that x is less than or equal to t. And the second probability we'll consider is a conditional probability, so make sure you're familiar with this, is the probability that x minus s is less than or equal to t, given that x is bigger than s. Now this looks a little bit strange, maybe intimidating at first, but let's just go through what it means. What is the first one? X here is still an exponential random variable, and we're going to be thinking of it as a kind of a waiting time, how long you have to wait. So maybe you can give physical meaning to this so this makes it more intuitive. So let's say, I've heard this with a bank problem. So let's say you walk into a bank and you are the first person in line. So let's say there's a window at the bank right here, and then someone is being served currently, and you're the next guy in line. And let's say the waiting time, so x is going to be how long a person takes at the window, is distributed as an exponential distribution. So first we're saying, what is the probability that the time they wait is less than or equal to this time t? And the next thing we're asking, let me put it in this way. Let's say you've been waiting for s minutes already. Okay, so you started at 0, you walked in, you got in line, and at time s, you're still standing there waiting for the person. Okay? So you're sitting there thinking, oh my, how much longer do I have to wait? And intuitively, maybe you're thinking that because I waited so long, I must not have that much longer to wait. And if we're in this world where these times are distributed exponentially, you would be wrong. Because we'll see that calculation in just a second. But so this means that x minus s, so what does this mean? This is the total waiting time, the total amount of time this person spends at the window, minus the time you've already waited. So in a sense, it is the remaining time you must wait. Okay, so you've waited s time, x is the total time, so maybe what if x is here? That means that you've already waited s time, so this x minus s is this extra time you have to wait when you make that thought in your head where you're like, how much longer do I have to wait? That much longer is x minus s. What is the probability that that time is less than or equal to t? So let's say this is t exactly. So what is the probability that we're in this range, less than or equal to t, given under the condition that we're already past s? Okay, so let's calculate both of these guys. So the first one is probably the easiest, the probability that x is less than or equal to t. Remember, if you want to find the probability that a random variable is less than or equal to some value, all you have to do is integrate the PDF, so the PDF from 0 till that value. So in this case it's 0 because exponential starts at 0. The PDF is given by lambda e to the minus lambda x dx, and we can easily solve for this. This is just lambda, we take the lambda out, we have the minus 1 over lambda e to the negative lambda x, 0 to t. So then this lambda negative 1 over lambda becomes a negative 1, e to the negative lambda t, and then we have minus e to that, we put 0 in here, we get 1. So it's really 1 minus e to the minus lambda t. That's our first probability. Now what's our second one? So this one's going to be a little bit more involved to calculate, but really not that bad. So we have, let's rephrase it first. It's going to be probability that x is less than or equal to t plus s, given that x is bigger than s. So I did it like this because I want the x alone, so I can do calculations in terms of it. Now this is conditional. I'm going to rewrite it using the definition of conditional probability. So it's probability that x is less than or equal to t plus s, and x is bigger than s, over probability that x is bigger than s. This is the definition of conditional probability. Good. Now this top part, x is less than or equal to t plus s and s is bigger than s, then that is, this part we can just drop, because if s is bigger than s, and now the second calculation, let's do it on this small sheet of paper just to keep everything clean. So I've rewritten it into this form because I want x to be alone so I can do calculations in terms of it. Okay, so the second probability is what? Using the definition of conditional probability, it's going to be x is less than or equal to t plus s and x is bigger than s over probability that x is bigger than s. This is just a definition of conditional probability. Review it really fast if you need to, but this is exactly what this conditional bar means. Okay, cool. So then let's look at the top part. The probability that x is basically x is saying the time you're waiting is less than or equal to t plus s, and it's bigger than s, means that it must be in the range. Let me draw your picture again. Here is s, here is, let's say here is t plus s. So the probability that your waiting time is between these two guys, or sorry, the probability your waiting time is less than here. That's what the first part is saying, right? The x is less than or equal to t plus s, and it's bigger than s, means it must be captured in that range exactly. So this is saying it's the probability that x is less than or equal to t plus s, but bigger than s, all over probability that x is bigger than s. Now this again, we're just going to turn to our trusty PDF, and we're just going to evaluate this guy. So it's going to be, first part, let's do the top, is integral from, and our bounds here are s and t plus s. T plus s, e to the minus lambda x dx, bringing the lambda out. Okay, so then here we have lambda, and then we have over lambda minus, that just bring that out, so just -1 there. And then we have e to the negative lambda t plus s minus e to the negative lambda s. Okay, and then that is just going to be e to the negative lambda s1 minus e to the negative lambda t, so e to the negative lambda t, and what I did was I took this -1 and I used it to flip these two guys, I did this minus this instead, and then I took out an e to the negative lambda s from both, and then what I was left with was 1 here and e to the negative lambda t here. And now the bottom is what? So the bottom, this is evaluated as, again, bring the lambda over here, this is greater than s, so it's s till infinity, e to the negative lambda x dx, this is just negative lambda over lambda again, so e to the negative infinity is 0 minus e to the negative lambda s. So we have a negative here, we just get e to the negative lambda s. So what we want is this divided by this. So this nicely cancels, and we get 1 minus e to the negative lambda t. Now that is very interesting, because that was exactly the answer to the previous question, which was, what is the probability that x is less than or equal to t? So we see, this is often called the memorylessness property. I can actually write that right here. So it's kind of a long word, memorylessness. Okay, this is called the memorylessness property of the exponential random variable, which is to say that it doesn't care how long you've been waiting. The amount of time you have left to wait is as if you just walked in, which is kind of sad, but our calculations show that it's correct. So it's saying that if you walk into that bank, you walk into that window, and you start waiting, and you think to yourself, just as you start waiting, what is the probability that I have to wait less than or equal to 5 minutes? And you get some number, and that number is here, with 5 plugged in for t. Then you wait an hour, and you're waiting an hour, and the window's still not clear for some reason. You think, wow, it's been an hour. The probability must be so high that it's less than or equal to 5 minutes now. Actually, it's not. It's the same probability you just calculated, under the assumption that these waiting times are distributed exponential. Now, that's a very shaky assumption, not really true, but this is very important if you do Poisson process, or if you do the Poisson process, which we may talk about if there's time, but you could look into that, and that the memorylessness property is very important in that. So needless to say, the exponential random variable is a very important random variable in our whole structure here, and we'll see how it relates to the gamma random variable when we talk about that guy.